thank you very much for inviting me. It's a pleasure to be here. My father, I just say this, was actually a physiologist, and he died when I was quite young. That's one of his papers, and I had the pleasure of meeting this chap who he co-authored this paper when he was a student. So it actually means a lot to me to be here and be asked. So thank you very much. So yes, as was introduced, I'm a professor down the road at King's College London. And one of the things we study is global fire from satellites. We tend not only to talk about wildfires because, as we just heard, there's lots of fire that is lit on purpose around the world for deforestation, for agriculture, and for other reasons. Wildfires is only one part of the picture. But they are very much in the news, and the story is that they are, in certain places around the world, increasing because of climate change, but they are also very much at the whim of human policy and the enforcement of policy. So it's possible to change the story as well. So we study fires from satellites, and what you can see here, this is kind of some satellite data. It's basically giving, it's a long-term average, grams of carbon per meter squared per year burned. Vegetation is 50% carbon, so if you multiply these numbers by 2, you get the amount of vegetation burned per meter squared. And you can see that basically all vegetated places on the Earth burn. That's basically it. There's hardly anywhere that doesn't burn. Places like Greenland where there isn't a lot of vegetation. Africa is very much the heart of fire on the Earth, but you can see up in Canada, as we've heard, and Southeast Asia, there's plenty of fire. You can see at the bottom there, indeed two-handed, this is Northern Hemisphere Africa up here, and you can see these are annual cycles of fire. So fire is very seasonal. It doesn't happen all the year. It happens during particular periods of the year. And in places like Northern Hemisphere Africa, it's basically similar amounts burning each year. Boreal North America we heard of up here in Canada. It's pretty variable depending on the weather conditions. And in places like Equatorial Asia we heard, Indonesia, it's super variable because they have deforested and cleared peatlands, as we heard, and that means these peatlands are like firelighters essentially, but they're still quite wet a lot of the time. But if you have a drought associated with El Nino, you get huge amounts of burning. Here are some statistics. These are all rather uncertain, but the amount of fire on the planet is roughly equivalent to the area of India every year. And 50% of all source particulate matter that we heard is probably produced by landscape burning. So we heard about Canada. One of the things these fires produce is smoke in very large quantities. And here we have in Western Canada over here, fires, very large wildfires. And we were over here at the time doing something else in Eastern Canada near the Great Lakes. And we woke up and thought, wow, there must be fires really close, but they weren't. They were 1,000 kilometers away over here, transporting the smoke to us. And in recent times, we've had things like New York. This is New York in the morning. This is New York in the afternoon, just by the transport of this smoke coming from these Canadian fires. And as we heard as well, it's even coming to Europe. We measure this stuff from satellites, and one of the things we try to do is quantify, essentially the ultimate aim is to quantify human exposure to wildfire smoke. So what we need to do first is basically work out how many fires there are, where they are, and how much material is being burned. And we do this using satellite data like this. This is a very large fire in California. And basically all this orange stuff is heat coming out of the fire measured in the infrared. And there is a relationship between the amount of heat coming out and the amount of smoke being produced. You can imagine that's pretty obvious. If you burn twice as much wood, for example, you produce twice as much heat and produce twice as much smoke. So we can measure the heat with infrared sensors on board satellites designed for things like cloud top temperature, or measuring the temperature of the ocean, and we can estimate the amount of smoke being produced. Here's a global map of data like this. For 1 month, you can see all these little red dots of fires all over the place. This is just one particular period in the year. Fire, as I said, migrates up and down Africa according to the climate, but this is one particular in the middle of the year, basically. Over here, India, etc., Southeast Asia, you see lots of activity going on. If you look in detail a bit more of this, it's not all wildfires, as I mentioned. Here is Delhi is somewhere down here, and in one particular period of the year, October, November, all the farmers in the Punjab decide to basically burn all the rice straw. That they harvest the rice, most of this material is not really useful for nutrition, so they try to get rid of it and the cheapest and quickest and the easiest way to get rid of it is to burn it. So they burn tens of thousands of fields all at the same time in 1 or 2 months, and this smoke produces this basically goes down the intergalactic plane and causes, perhaps at this time of year, 60% of the air pollution in Delhi, and we saw the effect of that on people's lungs earlier. Here is Indonesia. We heard about these peatlands. This is a picture of actual. I'm not sure I would go again, but I did go twice to Indonesia during El Nino periods, and you can see this is a peatland on fire. I never thought that you could actually mismanage landscape so badly as this. This used to be tropical forest and flooded, so all the forest has been cut down. This huge trench here has been essentially dug to direct water away from the peatland, so it's now quite dry, and when the drought happens, the top sort of 20 centimetres is dry enough to burn, so you can actually ignite it. Not necessarily on purpose, but fire is used for lots of things here. And so the fire's got into the soil. Literally, the soil is on fire. This has got seasonality as well. You can see that during these El Nino periods, these are some recent, well, relatively recent El Nino periods. You can see there's two fire seasons here. And the concentration of particulate matter in the atmosphere is absolutely astronomically bad. You hear a lot about this on the news. Singapore is complaining, that their air pollution is quite bad. I can tell you it's way worse in Indonesia. Not all of Indonesia, but quite a bit of it. This is wider Southeast Asia up here. This is not so much peatland fires, but more agricultural and deforestation fires. So we're working in a place called Laos, which I will talk about in a little bit. And this is a nice satellite image of this area during the non-fire season. It looks very pleasant. And when the fire season happens, all these little red dots are the fires, and you can see there's a huge amount of smoke all over the place, and for weeks and months, basically. And people are unable to escape this. And places it used to be India, I think, that had the most polluted cities in the world, but now some cities in northern Thailand, for example, are becoming, number one because of this kind of activity. So what do? We basically take these satellite data, measuring this, what we call fire-rated power, or the strength of the combustion from these infrared measurements from satellites. We do this globally every day, and ourselves and others have built a system, in this case it's called the Global Fire Assimilation System, that takes all these data, converts the heat output into estimates of how much material is being burned on an hourly basis or so, and then that is put into essentially the same kind of models that are used for weather forecasting, that it converts it into estimates of smoke output, for example, 40 different compounds, including PM2.5, PM10, etc. And then that's put into an atmospheric transform model that basically moves this material around in the atmosphere using a forecast model, so you can forecast up to 5 days ahead where this stuff is going to arrive and in what concentration. So you can look at individual events like the LA fires, or you can look at global activity as well. With these data, it's all free. This is a thing called Windy. You can go on there and have a look at the animation easily. Let me just start that again. Is that going to work? Yeah. You can look at the animations kind of online, but you can also download the actual data of this. So if you want to look at what the concentration of certain air pollutants are in a particular region at a particular time, you can download the actual data. So Windy here, these are all the fire occurrence and strength, so the fire-rated power values, okay? This is the atmospheric carbon monoxide concentration. You can see at this time Australia had huge burning, and this is the PM2.5 surface level abundance, so terrible in India, for example, at this particular time. So all those data are available very easily to the global community. A few years ago, a colleague and I did this work, which was basically mapping globally from those data what fraction of PM2.5 that people would be exposed to comes from landscape fire. So you can see, not surprisingly, it's very high in parts of Africa where there's not that much industrial source and very high fire sources, also in parts of Canada. Here we see Laos. That was one of the highest places in this fraction. Almost all PM2.5 comes from fires. Basically, the place is beautifully clean air most of the time because they don't have much industry, not many vehicles either. So we focused on some of this area for our subsequent work, which I'll show you in a sec. Here is the example of Indonesia, for example. This is a place called Palangkaraya, which is the capital of central Kalimantan down here. This is the output from that model over many years, showing weekly averages of PM2.5 that you would be exposed to if you lived in here, in this place. And you can see these values are very high. This is something like the WHO 24-hour standard for safety. And this is weekly averages. I was actually there. It went up to 3,000, over 3,000. Totally shocking. Now, the question is, are these modeled? If people are going to make health assessments from these kind of data, we have to know that these are correct, right, or reasonably correct. And this was actually a measurement done by the government, the meteorological department, but it was the only measurement in an enormous area, and we don't know really if this instrument is well calibrated or not. So we've basically taken it upon ourselves to buy lots of these things, small air quality sensors called Purple Airs. They're about $200 each. They measure all these different PM fractions, and we can basically go and put these in the locations where we want to study to check that these model data are correct, and then basically get some confidence of using those in health assessments. So we've put dozens of these in what we have a combustion chamber, where we can expose essentially them to the same amount of smoke and understand if they give the same output. And we also put them all over, in this case Palangkaraya, we put them on health centres. We put 10 of them in this city here, which was home to a couple of 100,000 people. We also set up something called a mini-vol, which basically sucks smoke through filters for 24 hours at about the same rate as you breathe. So this is what your lungs essentially might be getting over 24 hours in this environment. And we can basically compare the Purple A data to these data to get a calibration factor. And basically, it turns out that you have to divide these sensor data by 2 in order to get true PM2.5 measurements from landscape fire smoke. The reason is that the instruments work on laser backscattering. They basically are proportional to the number of particles, and the density of the particles that they use to calibrate them is much higher than wood smoke. Okay, they're calibrated with dust, basically. So you have to divide the values by 2. This is, in Kalimantan, we see, this is the Purple Air data now from our 10 sensors averaged, okay? And this is the CAM's model output. And you can see that basically, as we heard earlier, the fire season goes on for months in this kind of place because there's nothing to remove it. There's no rain, there's very little wind, and these peat fires are going on for weeks. So it just hangs there. And in fact, the model gets a really good estimate of the magnitude, right? The grid cell is about 80 kilometers, on a side. So we thought the model would not perform well, but actually it does perform well. So we can start trusting these kind of data within limits for health impact assessment. And we also went on further, I'm not going to show it now, but we instrumented pregnant women with a PhD student of ours with personal exposure meters to see how much they were actually exposed to, not only that was hanging in the air, but what were they exposed to when they went through their day. These are the US Air Quality Index outputs. And the final thing is that I don't know anything about epidemiology, but I did work with some epidemiologists, and they use these data along with a whole host of health records from the WHO, paired studies with related to child deaths. So my understanding was that both the pair are basically having the same lifestyle factors, except one of them was exposed to large amounts of landscape fire smoke. And in this study, we came up with this exposure response curve, basically, and it turns out it's non-linear. So basically, as you're exposed to more and more PM2.5, the effect becomes increasingly worse. And then if you multiply this dose response function by the populations, exposed populations in these areas, and all the model output of the concentrations, you get huge numbers of predicted deaths, excess deaths. This is for children under 5. And the results of this were that almost 1 in 10 deaths in children under 5 worldwide are associated with breathing in smoke from landscape fires. That is not smoke from burning wood in houses, it's outdoor fire smoke. And almost all of it is in low and middle income countries, and almost all of it is associated not with catastrophic wildfires that we can't control, but fires that are lit on purpose for deforestation and agriculture. So there is something that can be done about that. We used to do that in Britain, and we don't do it anymore, so something that can be done. Okay, that's all. Thank you very much.